Hello everyone, I'm João from That's Brilliant. In this video, you're going to see the mathematical proof of the derivative of logarithmic functions. So, when you study calculus, we see that the derivative in respect to x of log base a of x is equal to 1 over x times natural log of a. And a here is just a constant. We are using a generalized base. It's just a constant to represent the base. And this is the derivative of a logarithmic function. And we're going to prove that this is true. So how we are going to prove? Let's rewrite this part here. So gx of log base a of x. And now we are going to use the change of base property of logarithms. We see that we can change the base. It's a property of logarithms, and we can choose a base. So what's going to happen is we have, this is the derivative in respect to x of log some new base of x over log the same new base of a. This is the property, the change of base property of logarithms. And what new base we're going to use here? Well, we're going to choose the e, the number e, the e as a base. E is the number of Euler. It's 2.7 something. It's an infinite number, and it's a constant. And this number appears a lot in calculus, and we're going to see in the next video why is this number so important to calculus. Why did we choose this number? Well, we chose this number because we know that choosing this number, the mathematical proof is going to be correct. It's going to work. But we're going to see in the next video that this number appears in calculus naturally. We chose it here because we know that it's going to work, but it appears naturally in calculus, as we are going to see in the next video. So we changed the base, so it is the derivative in respect to x of natural log. We can rewrite this as, for example, if we have log base e of x, this is equal, it's the same thing of natural log of x. If we say natural log, it's implicit that the base is the e. So I can rewrite this as the derivative in respect to x of natural log of x over natural log of a. And remember that a, in the beginning, we decided a is just the base of the initial logarithm, but it's a constant. So we can, just to make all these steps, we're going to write this as being gx of natural log of x times 1 over natural log of a. It's the same thing. I have just put separately this natural log of a. And as we have already discussed, a natural log a is a constant. So the logarithm base e of a is constant because e is constant and a is constant. So all of this here is constant. So we see in calculus that it's already, we studied this in calculus, we see the mathematical proof that if we have a constant multiplying the function inside a derivative, we can take the constant out of the derivative. So, writing mathematically, it's saying that 1 over that is equal to 1 over natural log of a times derivative with respect to x of natural log of x. So again, we have a constant inside the derivative. We can take the constant out of the derivative. So here it's multiplying, it's the derivative of a function multiplied by a constant. So this is equal to the constant multiplied by the derivative of the function. So this is equal to this here. So this derivative here, it's very famous. And we study in calculus. and we're going to have future videos on that proving this mathematically, that the derivative of natural log of x is 1 over x. So let me write here, the derivative with respect to x of natural log of x is equal to 1 over x, or x to the power of negative 1. So we can rewrite this as being 1 over natural log of a times 1 over x. So this is equal to 1 over x natural log of a. And here we have mathematically proved that the derivative of a function, of a logarithmic function base a of x is equal to 1 over x multiplied by the natural log of a. And as I said, we're going to see the mathematical proof of this in future videos. And I say again, in calculus, then the number of Euler appears a lot of times, and it's very important to calculus. But why is it important? Well, we're going to see in the next video that, and I'm going to put the link of that video in the description below, that this number appears naturally in calculus. This number is defined as a limit, and it appears naturally in calculus. Here we chose the number of Euler because we know that the next step we're going to have the derivative of a function that we know the derivative very simply. So we chose this base. Think about that. If we choose this base, this mathematical proof works. So this is why we chose this base. But it appears not only because we choose, but this number appears naturally in calculus. And it's because of this that it is so important. So that's it. Thanks very much for watching, and I'll see you in the next videos.